so good morning to everyone. Morning, lads. How very friendly. Right. Okay, so welcome to Lecture 2. We'll just let a few more people join. Okay, so I'm looking at the comments now. Again, if someone could just let me know that you can hear me, that'd be great. Great, thank you. Fine. Right. So some of you asked if I could just quickly go over superposition again. Where can we get the lecture slides? What? They're on the notes page. I'll check that they're there, but they should all be there. Certainly last year's anyway. If not, I'll upload all the new ones shortly as we go along. But the majority of the slides will be on the notes page, which you can get to from Blackboard or from the notes page. Okay, so superposition again. Right, let me just get me to the place where I can change my slides. Right, we're off and running. Right, so just to recap on the superposition then. This is to do with the linearity, and it's to do with the ability to break a circuit into chunks by source, whether it's a voltage source or a current source. Only look at the response to that particular source and then add up the resulting answers, and that gives you the whole thing. So in this way you can break a circuit down into simpler areas which you analyze separately and then just add them together. And it only applies to linear networks. And a linear network is one where this expression down here applies. So let me just get a pointer up. Right. So this, when I say this, I mean this one at the bottom. fx1 plus fx2 is equal to the sum of the two. So we could split this complicated output into two simpler outputs. And superposition allows us to do that, but it only works in linear networks. So the easiest way to do this is by example, and we looked at this at the end of the last lecture, but experience tells us that at the end of lectures people have lost a bit of interest, so worth going over it again. We've got a source and it's driving a current, and we're assuming it's going in this direction for definition purposes. We've got another source, current source, and again we're assuming it's driving current in this direction, and it's asking us to work out what expressions for I1 and I2. So I1 is this current going through the resistor, and this current here is I2. So we look at this and we go, actually we're a bit confused by this, looks a bit complicated, no real idea what's going on, seems to be too many variables. But let's apply this superposition idea. Let's not panic. Let's split this down. We've got two sources. We want to just get rid of one source for the time being and see what's going on, and then we can analyze a simpler circuit, and then we can do the same thing to the other source. So we suppress the source, and in this case this means replace it with its internal resistance or impedance. So in the case of a voltage source, we suppress it by replacing it with a short circuit, because its series resistance ideally would be 0. And in the case of a current source, we would suppress it and replace it with an open circuit because its equivalent impedance is very high. So look back at independent sources if you want to get an idea of where that might come from. So let's suppress the current source. So this is the current source. We suppress that, we replace it with an open circuit, which means we just sort of take it out. That leaves us then with this potential divider. If we redraw the circuit like on the right hand side, we've got the voltage source which we haven't suppressed. We've got two resistors left, which is what we get if we've taken this source out by replacing it with an open circuit. And now we can see this reduces down to a potential divider problem, and we can apply Ohm's law, and off we go. So then we go back to our original circuit. We now suppress the other source, and in this case we have to suppress the voltage source, and we replace the voltage source with a short circuit. So we redraw the circuit with the voltage source replaced with a short circuit, so it's just a wire straight through. And now we can see that this is a current divider circuit. So we can apply the current divider equation, or you can work it from first principles, it's not that hard, and we can work out what the various currents would be in this particular circuit. And then, because it's a linear circuit, we can add those two responses together. So here's the response for current source suppressed, and here's the response for voltage source suppressed, and this is the answers for voltage source current source suppressed, and this is the answer for current source suppressed. So to get the total current, we just add I1A and I1B together, and that gives us this current here for I1, and likewise I2A and I2B added together, which are these two here, gives us the expression for I0. So they're actually reasonably complicated expressions, but by doing it in a superposition way and not panicking, we've got to the answer quite quickly, and it's relatively straightforward. So this leads us on to a couple of theorems, the Norton and Thevenin theorem, and you'll be hearing about these a lot as we go forward. So this is two things that you really need to know going forward, and it comes from the theory of superposition. Right, so what I'm going to do is going to make it big like that now. So we don't want to waste space looking at me when you could be looking at this. Okay, so we start with something called a source transformation theorem, and this is a theorem that allows us to transform a voltage source and equivalent circuit into a current driven circuit. So we can swap between them. So if we don't like the idea of a voltage source driving a resistance, we can actually turn it into a current source driving resistance in its equivalence. Under a certain set of conditions, and we have to be careful about that, these two circuits will be identical as far as the circuit is concerned. Okay, so theorem. A voltage source V in series with a resistor R can be transformed into a current source I in parallel with a resistor R, with the current source, this is the constraint, the current source having a value I equals V over R, where I, the current source here, is the value of V, the voltage source that you've got in your original circuit, and R, the resistance in the original circuit. So we've transformed. So remember, this looks like an ideal or a practical voltage source. It's got an internal impedance and whatever, and we can turn that into, for modelling purposes only, into an equivalent current source or a practical current source with a resistor. So these two circuits, which are sources, are mathematically identical. Yeah, they're not obviously not physically identical, but mathematically, in terms of analysis, they are the same. So this is where it starts to get abstract. You start with one circuit and you turn it into another circuit for analysis, and it gives you the same answer. Okay. Oop, going the wrong way. And the proof of this, it's very straightforward really. Again, it's slightly abstracted. We've got a voltage source, it's driving a current, we'll have some kind of load here, and what we're interested in is the value of the voltage at this point here, so the output voltage. So if we make it into a loop by putting some arbitrary load on here, we can say that minus V plus ISR, which is the voltage dropped across there, plus VP across here must add up to naught, which is Kirchhoff's law. And then we can say that VP, the pole voltage, if you like, or the output voltage, is equal to V minus ISR, just by rearranging that. And then we can look at this circuit and we can apply the same kind of current law type of thing. So we've got IX plus IS minus I. Again, this is an arbitrary load that we've just applied here. Equals naught, because what goes in must come out, which must be that then IX equals I minus IS. Okay. VP equals IX times R. It's got to be IX times R, that's the pole voltage, and therefore we can rearrange that and substitute in to get us this. And these two equations, VP for this one and VP for this one, are the same if we define V, this bit here, as being equal to IR, because then this equation and this equation are then identical. So as long as we make sure that V equals IR or I equals V over R, which is the same thing, then these two circuits are equivalent to each other. Okay, and then we can obviously replace this type of circuit or feature in our circuitry with this type of feature if we want to analyze it in a slightly different way. And we'll do that as we're going along, so it should become clearer if it's not clear at the moment why that would be the case. So this leads us on to two very useful theorems. We've got Norton's theorem, states that any two-terminal circuit containing voltage, current sources and resistances is equivalent to a single current source in parallel with a single resistance. So you can take a mishmash of all kinds of circuits, and as long as it's only got two terminals coming out of it, you can turn it into an equivalent source and one resistor. And Thevenin says the same thing. Any two-terminal circuit, so that any two-terminal circuit containing voltage, current sources and resistances is equivalent to a single voltage source in series with a single resistance, which means you can simplify things down really easily. And simplification is usually, so it's always a good idea, usually a good idea. So what does that mean? So in pictures, the Norton equivalent is you've got a black box, you don't know what's in the black box, someone's told you it's got resistors, voltage sources, current sources, it can be as complicated as you like, but all you've got to play with are two terminals coming out of it. So the question is, what's in this box? Does this hold for complex load? It does hold for complex load, but it's slightly more complicated because there are issues with what's the word? Conjugates, that kind of thing. So you just have to watch those. Right, so we can turn our black box into an equivalent circuit, and we have a choice of equivalent circuits. We can either say this whole thing, whatever's in here, is the equivalent of one current source and one resistor, and this is a practical current source, remember. And in the Thevenin case, we can say that the black box could be the same black box. All we know is it's got two terminals, A and B. We can model that as an equivalent voltage source and a resistance in series. Okay. Can you go back to the definitions? The definitions of what? Norton and Thevenin. Okay. Okay. So the words here, which I appreciate there are a lot of words, but it's the definition, and the words here as well are the same as the picture. I'm going to move on to the picture now. So this is the theorem definition in pictures. Okay, whatever's in your black box can be described by a current source and a resistor. Whatever's in your black box can be described as a voltage source and a resistor. Okay, so just get that get that concept, because this means that whatever's in here can be simplified down to just this. Okay, so how do we know what's in the box then? Or how do we actually get the value of this source and this resistor here? So this equivalent voltage here is equal to the open circuit voltage between A and B. So if you measure the voltage across here, this tells you what this voltage is here. Because remember, no current will be flowing if you just measure the voltage. So the voltage here must be the same as the voltage here, because there's no current through this resistor. So no voltage dropped across that resistor. And R Thevenin, in theoretical terms, is equal to the resistance between A and B with the sources and terminal of the black box suppressed, which is a bit of a key. But if you could see that if we could suppress this and replace it with its short circuit and just measure the resistance across here, then we would work out what R Thevenin is. And remember, this is for all complicated stuff in this box. This idea holds. It's a bit tricky with dependent sources. We don't necessarily know what dependent source is yet, so we just have to bear that in mind. So that's just a sort of a reminder to me, really. Equivalent Norton with the current source is the same kind of thing. If you look at this logically, we can say that IN the value of the current source is equal to the short circuit current between A and B. So if we short circuited this and measured the current that flowed, we would get the value of this current source. And Rn is equal to the resistance between A and B with sources and turned to black box suppressed. So again, if we suppress this current source, we replace it with an open circuit and we're just left with a resistor to measure. Okay, so just accept that we can suppress current sources at the moment. So, some consequences of this. It should be apparent that Rn equals R Thevenin. Okay, and if we're not sure what Rn and R Thevenin are, this resistor and this resistor are actually the same values. And I'll leave that for an exercise for you to show that if you are concerned about it. And for a two-terminal network, the resistance that you get is the open circuit voltage over the short circuit current. Okay, just applying Ohm's law to it. Right, example. A two-port black box has an open circuit voltage of 2 volts because we've measured it with a meter. It has a short circuit current of half an amp because we've measured that with another meter. Its resistance is therefore 2 divided by 0.5, which is 4 ohms. Okay, so two simple measurements here of its open circuit voltage, its short circuit current, tells us that the equivalent circuit in this box is equal to this, or equally valid is equal to this. Okay, so there's a lot of words, a lot of concepts, but the implementation is very straightforward. Yeah, it's just an application of Ohm's law. And there are various other ways of trying to get to this answer. Remember, all the answers should be the same. We can apply a test voltage at the output terminal with independent sources suppressed and measure the resulting current. So this is sort of a thing that you sort of do theoretically. The output resistance is then given as the ratio of V test over I test. So that's another definition, another constant. Where does this come from? Okay, so if we take our Thevenin circuit and if we suppress the voltage source, so we replace the voltage source, replace it with a short circuit, then we're left with just a resistor. If we then, so this is the equivalent circuit with it suppressed, if we then just apply a voltage at this end here, a current will flow and the slope of the IV characteristic will be related to the resistance. So we're just looking at Ohm's law in a graphical form there. So these are lots of different ways of coming to the same answer. So this brings us to quite an interesting concept, and it asks us to think about resistance a bit more, because what we're looking for is the slope, because that's defined by the resistance and we're trying to find the resistance. So one way of thinking of resistance is rate of change of voltage with current. If we change the voltage, how quickly does the current change and in what form? So if it's a linear system, it's a straight line, and that gives us a VI, a slope of a straight line. One point of such a straight line is always 0, 0. With a resistor, we know it's going to go through 0, 0. The other is just some value of V and its associated value of I that's somewhere on the line, which could be anything, and that we have our applied voltage and we measure the current. And then the slope is just the gradient between those 2 points, but one point is implicitly 0, 0. So we could take, apply any voltage we like, measure the current, and that's enough because we know there's a straight line. So we've assumed there's a straight line and it's going down to 0. That holds for a lot of cases, doesn't hold for all cases, but the principle of you only need 2 points to measure the gradient of a straight line is very important going forward, because when we come to look at dependent sources, that's something we have to bear in mind, and it's a lot of students tend to forget that you're looking what slope you're actually trying to measure. So always ask yourself, if you're trying to measure a slope or a resistance, what resistance are we talking about? Is it a static resistance or is it a dynamic resistance? And we'll talk about dynamic resistances a bit later. So this is the practical way of doing it. We can apply an adjustable load, if we like, a variable resistor, and change its resistance until the voltage across it is half the open circuit voltage. Okay, and this is what we do in some of the labs after Easter. So here's our circuit that we don't know what the values are. We don't know what the value of this resistance is. So what we can do is we can measure the voltage with no load attached. So we measure the open circuit voltage, and then we attach our variable resistor, and then we adjust this resistor by twiddling its knob until the voltage that we measure across these 2 points is now halved. And then from the voltage divider equation we know that if this voltage is halved, then the value of this resistor must equal the value of this resistor, because if half the voltage, these resistors must be the same. And that comes from the voltage divider equation. Now you can take away R, you can unplug it, and you can take it away and measure it, because remember, you've got control over anything to the right of this AB terminal. You haven't got visibility of anything to the left. Okay, so that's the practical way of working out what the impedance is. So someone's asked, does this still apply if there are capacitors, etc. in the box? It does apply, but it only applies at AC, because capacitors look like open circuits at DC. So you can apply it at AC, but it's just a little bit more complicated. But yeah, it all applies. Yeah, okay, it simplifies the resistor being a complex component. Oh, and that's all you got to do is replace R with Z. And there you go. What you get is a short circuit current at AC. Yeah, so it only operates at certain frequencies. You've got to model this at a fixed frequency if you've got other components like capacitors and inductors in there. Because at DC, which is what we're sort of considering at the moment, at DC, capacitors are open circuit and inductors are short circuits, because inductors are just basically pieces of wire. They only do something useful when they've got an AC flowing through them. Okay, so we're not worried about AC at the moment. We're just worried about DC. Right, mesh analysis. So this is starting to get a bit more useful now. So I had a look at Paul's first lecture, and he introduced the idea of mesh analysis, if you haven't seen it before, with Dan and Neil. And he showed that he did some quite complicated work with differential equations and modelling those as well. So if you understood that, then that's absolutely great. But if you didn't really get what Paul was trying to explain at that point, then we're going back a little bit. If you understood mesh analysis, you can sit back and relax for a few minutes. So mesh analysis. Mesh analysis is a useful circuit analysis technique which can be applied to many types of circuit. It can be routinely applied and does not require the use of circuit analysis tricks. It cannot be applied to non-planar circuits. So what does that mean? A circuit is planar if it can be drawn on a plane, okay, a piece of paper, in such a way that no branch passes over or under any other branch. You can't have things looping over the top or going underneath. If you can draw it like that, you can apply mesh analysis. In practice, you can draw nearly all circuits like that if you start to apply these Norton and Thevenin transformations to remodel your circuit to a different form. Right, so here's an example. A circuit with only voltage sources and resistors. Here's a voltage source, here's another voltage source. We've got a collection of resistors, and we'd like to know what the currents are and the voltages in this circuit and the nodes are. So the way to solve this problem is to assign a mesh current to each of the meshes in the circuit in a sensible direction. And for me, sensible is clockwise, but you can define it wherever you like. So here's our mesh current I1, here's a mesh current I2. Apply Kirchhoff's voltage law to each mesh in turn, mesh 1 first, then mesh 2, etc. and gather together the current terms in the resulting equations. So we're just applying the basic rules that we've understood before. So what does that look like? Okay, so there's another note here on mesh currents. Mesh currents and branch currents are not necessarily the same thing. Branch currents are real. You can measure them if you put a meter in the loop, but mesh currents not necessarily, and we've looked at that before because this mesh current here is not the same as the branch current, which is the mesh current in this case, is not the same as the branch current down here. So there's something going on in the definitions of mesh currents. Okay, but we've talked about that before, and it's nothing to get too worried about. So the solution to our equation, mesh 1, we go voltage source, resistor, resistor. So we've got the voltage, so we just add up all the voltages around the loop and add to naught. So we've got -2 because direction here. We've got 2I, which is the voltage dropped across this resistor here, and then we've got 4, which is the value of resistor, I1 minus I2, because remember we've got this mesh current circulating this way and you've got this mesh current circulating this way, and they add up to be 0. And this is the only tricky bit in here. And the solution for mesh 2, 4I2 minus I1, which is the equivalent voltage due to the currents in this element here, 6I2, yeah, plus 4 from there, plus 2I2, 2 being the value and I2 being the current thrown, equals 0. So now we've got two equations in two unknowns, I1 and I2 being the unknowns, and two equations here. So we can gather these together and get them into a sort of a common form. And this is very common throughout engineering, is we try and squash things into a common form, because then we can apply common solutions or common techniques to try and solve it. So in this case we would put it into the sort of logical form with I1 and I2 equals something, and again I1 and I2 equals something. So now we've got two equations in two unknowns. Why does V source in both meshes be positive? Well, it isn't, is it? It's -2 here and it's 4 here. Yeah. Right, so we got two equations in two unknowns. Simultaneous equations are, it's two simultaneous equations, so we can solve one. There are many ways of solving simultaneous equations. This is just now a mathematical problem. Okay, so we've taken our circuit, we've analysed it, and we've reduced it to a mathematical equation, which we can solve by whatever method we choose. So in this case, it's trivial to solve it, so we can just do it by substitution. So we get a value for I1 from the second equation, just rearrange this to get I1, which is 3I2 plus 1, and then substitute that value of I1 into the first equation for I1 here. So it's gone in there, and there's the individual working. So I'm a big fan of writing down all my interim steps and showing my working. This is something I was taught at school and I've never got away from it, and I find it really, really useful because I tend to make mistakes in algebra. So if I put down all the steps, hopefully I've got more chance of actually getting to the right answer. Might take me a bit longer, but it gets there. So in my slides, what I tend to do is put down all the interim steps, because I'm assuming that some of you at least are going to be like me when I was young, and therefore you'll be grateful for the interim steps. But I know that some of you will also be able to look at these equations and just go, oh, I know what the answer is. So you might be wondering, what's the point of having all these interim steps? However, when it comes to courseworks and exams and things, bear in mind that I am interested in the working and the interim steps, and you get marks for that. So get into the habit of writing down, at least for me, any interim steps and workings, and explaining what's going on. Use words like make the substitution for I1, so I'm not having to guess what you're trying to do. And when you come back and look at your revision notes or your things in a few months' time, you won't be guessing what you've done either. Okay, so before I get the inevitable complaints about there's too many slides and there's too many equations and it's all that, the whole point of it is really that you can use these for revision later, because all the interim steps will be there and you won't be asking yourself, how did he get from here to here in one go, which is the problem I had when I was at university. So that's just the way it is. It's going to be good for some of you, and for others you're probably not going to like it, but that's just the way it is. Okay, so is there a formula sheet or something similar for the exam? Not normally, no. There are not normally any formulas that really need to be memorized, but you know, I might expect you to memorize Ohm's law. I don't think that's unreasonable, and that wouldn't be on a formula sheet. Okay, if you don't know Ohm's law by the time you get to the exam, then there's no hope for you. Okay, right, so that's a simple way for a set of simultaneous equations, which is very straightforward. Simultaneous sets of equations can be a lot more complicated than that. So one of the things I will do is try and teach you a general way that is possible to do with a pen and paper in a simple way, and it's something I find useful, at least because quite often we don't have computers lying around and all we've got is an envelope and a pencil. We need to try and work things out. So there's a method called Gaussian elimination. It's one of the methods that computers do to solve big sets of equations in well, not one go, but to break them into simple things and go with it. And so it's worth looking at that, I think, just to get an idea of how to do this. So you'll be armed with a tool that's a bit practical, at least. So what is Gaussian elimination? Gaussian elimination is a systematic method for solving matrices which eliminates unknowns until one equation contains only one unknown. So one equation with one unknown is solved. Okay, and then once you know what that unknown is, it becomes a known, and then you can put it back into the previous equation and work backwards. An example will show that shortly. So we try and turn our system of equations into the form shown below. So this is the form shown below, and it's a matrix equation. And what we've got here is a matrix, and the interesting part here is that this bit is in a special form, and it's got zeros here and only one unknown in that row. And here we've got two unknowns in the row and a zero, and then we've got all three. So this is called echelon form. And if we can manipulate our set of equations into this form, then it becomes very easy to work out the answers, because if everything's zero in this row, for example, we just know that it's going to be f times I3 equals j. And that's job done as far as we're concerned. And then if you know that one, you can work back through the rest of the system. Comes into its own when you get systems of 3 or more equations. So we've only got 2 equations, but we'll stick with 2 equations just to demonstrate the principle. There are loads of ways of solving 2 simultaneous equations. So we need our equations in matrix form, and this is quite easy to do because, as I said before, we try and shoehorn our systems into a common form that we can work with. In this case, the common form is to have the 2 variables, or however many variables we've got, in order in both equations. So we've got I1, I2 equals something, and I1, I2 equals something. And we can turn this into a matrix by just taking these coefficients and putting them into the corners of the matrix. So we just literally just copy them straight over, and then we've got our input variables in a vector I1 and I2, and then the right hand side just becomes 2 and minus 4. So that's in matrix form, and now we can solve that with any matrix technique that we're interested in. So you can do it by determinants, you can do it by MATLAB if you happen to have a computer available, or we can do it by this Gaussian elimination if all you've got is a bit of paper and you can't remember how to work out determinants. It's very straightforward. So to solve this by Gaussian elimination, we can start to manipulate this, because remember, we're trying to get this part of the matrix into echelon form, which means we've got to do some transforms or something on it, and they're very simple transforms we can do because it's linear equations. We can multiply top row by 2 and the bottom row by 3, for example. It doesn't change the maths, it just changes the numbers a bit. So if we do that, multiply that by 2, we get 12 minus 8, and remember this one is 4, and multiply this one by 3, so 4 times 3 is minus 4 times 3 is 12, 12 times 3 is 36, and 4 times 3 is 12 with a minus. Now the first columns have numbers the same, so we've transformed this. Yes, you can do that, but if you've got a matrix that's 4 or more bigger, then left multiplying it in your head is going to be, or on a bit of paper, is actually quite complicated, right? So okay, so just to recap, we're doing it with a 2 by 2 matrix just to show the principle. I'm not suggesting that this is the best technique for a 2 by 2 matrix. Okay, so first column have numbers the same. So now we move on. We can make a new row 2 by adding the old rows 1 and 2 together, because it's a linear operation. So if we add these 2 rows together, we can make a new row 2 which you can substitute in. So that becomes 12 plus minus 12 equals 0. Minus 8 plus 36 equals 28. 4 minus 12 becomes minus 8. So that now becomes our new second row. And you can see now that by just simple transform, by multiplying and adding, is all we've had to do. We've ended up with a system with this matrix in echelon form. And now it's easy to solve, because we can look at this and we can just go 28 times I2 is equal to minus 8, therefore I2 equals minus 0.286. Then we can solve the first row by, because we know what I2 is now, we can just say that 12I1 minus 8I2, and I2 is 0.286, is equal to 4. And we can work out I1 from that. So we've managed to simplify it down into lots of little simple equations rather than one big one that we've got to solve in one go. So in summary, given a system of linear equations expressed in matrix form, AX equals B, you can carry out a series of elementary row operations as needed. We can interchange any two rows without changing the fundamental maths behind it. We can multiply a row by a non-zero constant, any constant you like, and we can add a multiple of one row to another row. All this does not change the fundamental equations because it's linear. And we aim is to reduce the matrix to echelon form, and then we can get easy solution by back substitution. We haven't had to calculate any determinants or anything else, and calculating determinants for anything bigger than the 2 by 2 matrix by hand is a process fraught with disaster in my experience. So for this course it says we won't go into any more complicated than 2 by 2 matrix. Actually we will. We'll go into 3 by 3s, but we look at some tricks for trying to simplify those down as well. So you can get into the habit of solving this way if you want, or you can apply any method other that you're happy with. But that's the use of matrices as far as I'm concerned. Right, so returning to our problem then. We can put, this is the set of equations that defines this problem. We can look back at that. We can see that we end up with, if we put that diagonal down here, we see we've got symmetry on either side of this diagonal, and this obviously works as well for sequences of bigger matrices with more meshes involved. You can see this gets complicated very quickly the more meshes you have. So the resistance matrix is symmetrical about the major diagonal. So here's the major diagonal and here's the symmetry. They're both minus 4. The terms on the major diagonal are all positive. So these are little tricks to make sure you've actually managed to construct your matrix correctly just by looking at it. And the terms off the major diagonal are either negative or 0. So if they don't abide these rules, then you've created your matrix wrong. You've made a mistake somewhere in your algebra. So these are just ways of just testing what's going on. Now the right hand side of the matrix equation is the sum of all the voltage sources around each mesh. Okay, and the positive major diagonal terms represent the sum of the resistances around the given mesh. So in this mesh here we've got 2 plus 4 equals 6, and here we've got 4 plus 6 is 10 plus 2 is 12. So we can start to see that maybe we can start to construct these matrices just by looking at the equation. The off diagonals here are what's common to both meshes. So minus 4 is common to this mesh and this mesh. So that's what goes into those things there. The negative off, okay, let's done that. Right. Why was the minus 8 multiplied by I2 and not minus 1? Well, it could be that I've just made a mistake in the writing of it down. On the part solving first, I don't know. We'll look at that later, or you can look at it and you can tell me why. Should be all right. Right. Always check your answer. So that's very pertinent, isn't it? Could be that I've made a mistake, Sam. So you never know. We'll go back and check that at some point, and I'll report back on that. Very easy to make arithmetic mistakes when analysing and solving circuits. Very important always to check your answers, particularly if you're then going to build a circuit based on it, because modelling a circuit is easy, building a circuit and changing it is much harder. So for mesh analysis, we can do this by checking Kirchhoff's voltage law for a selected mesh. So here, voltage across the 2 ohm resistor in mesh 1 will be 2 times I1. So we've calculated what I1 is. It's 1.143, so twice that is going to be 0.285. And the voltage across the 4 ohm resistor will be 4 I1 minus I2. So we put the numbers in again, work it through, and we end up with 4 times 0.429, which is 1.715. And if we add those two together, around the voltage across here and the voltage across here should add up to 2, and in this case they do. So whatever's happened back on the slide, it's correct, because the answer has been checked and has turned out to be correct. Might have dropped a sign in the working, I suppose, but you never know. Right, and then we can move on to nodal analysis, and what I suggest we do is stop at this point, 42 minutes in, and then we'll pick up nodal analysis next time. We'll go through that a bit quicker because it's basically the same as mesh analysis, and the two together are just applications of Kirchhoff's voltage law and Kirchhoff's current law, and they're very similar, but we'll pick that up next week. So thank you very much for listening, and I will check Sam Stevens' query about that, and I'll get back to you on the answer for that later. Okay, bye for now.